Okay, and we are recording. And I think I should be sharing my screen. If anyone doesn't see it, please let me know. So if I can get everyone to start by going to the Google Draw page, I sent a link in the chat. I'm going to do something a little bit different today with the Google Draw. I gave you a whole bunch of objects. Along the left, we have some point charges. Those are the pink and green circles. We have some parallel charged plates, and I've grouped them so you can click and drag one at a time. And we also have these things at the bottom that I don't know what they look like, kind of like the wheel on a pirate ship. These are a charged sphere, so that's the pink circle inside. Oh, sorry, that's my phone. Inside a charged shell, and this was actually a shape that we were kind of that we discussed in a PAL session. I think it was last Monday. So this is a system you've seen before, but we haven't really done many calculations with it. So the idea today is that I've given you these different charged objects, and I want you to create some systems. And I'll go through the descriptions of the systems I want you to make in a minute. And what we'll do is, depending on what systems you come up with, once you've finished building your systems, I'll go through and do a couple sample calculations. Things like, if you have a system with a high potential energy, or I guess I should be a bit more specific, because technically you can define potential energy how you want. So if you have a system where you've maybe placed a point charge inside an electric field of a capacitor, for example, and if you were to release that point charge, it would move in such a way that the energy of the system, the potential energy of the system, would decrease, then, for example, we could calculate what would the final velocity, or I guess the final speed of the particle be. Maybe your system, you've done some work on an object in your system to put it in that configuration, in which case we can calculate what was the potential difference as you did that work. So can everyone claim a spot? There's 4 kind of compartments that I've broken it up into. Okay, so we've got a platypus taking this second slot here. Someone else taking a smiley face. Cool, I like it. Okay, just so we don't have people building on each other's things. So I would like for everyone to make 3 different systems in your slot using the objects that I gave you. Or if you like, you are more than welcome to use your own. So you can use this sphere and shell system. You can use capacitors like parallel plates, and you can use point charges how you want. And I want you to make 3 individual systems. The first system is where you set up the system a certain way. And I have these written at the top here. So this first system is a system where the potential energy is such that when you release the system, or like you stop influencing it, the potential energy would decrease. So maybe a positive charge moves to a region of lower potential, something like that. The second part, or the second activity I want you to do, is to actually show your system twice, or show an object in your system twice, as like a before and after of you doing something. And so I want your system to show before and after shots, where to go from the before to the after configuration, I guess, work was done on a point charge. So maybe you moved a particle within an electric field. Maybe it has been moved closer or further to another point charge, things like that. And the third one, the third system I want you to make is a system that is in its preferred energy state or its lowest potential energy state. Meaning that if you, this is also called a stable equilibrium, kind of. I guess that terminology is used for something a little bit different. But I want you to make, so this third one, I want you to make a system that everything is happy. If you can put the system in this configuration and you let go of it, it's going to stay there. So take some time. Put questions in the chat as you have them. And let me know when you are finished. We'll say let me know when you're finished the first system to start. System where a potential energy would decrease if you were to release it. I'll give you a ready to continue message in the chat for this system. Okay, looks like we are ready to continue. So, okay, everyone pretty much did the same thing. Nice. Full points for consistency. We've got a positively charged, like a positive point charge close to a positively charged plate. And yes, if you were to release that, it would be repelled from the positive plate, attracted to the negative plate. And so that means it's the potential energy of the system would decrease as it moves down or to the right, depending on the orientation of your capacitor. Nice. Okay. We like the capacitors. Cool. Good. So now I'm going to yank you out of your comfort zones a little bit. So next system we're going to make is where you have a before and after picture of a system where work was done on a point charge. And I want to be more specific. Excuse me. And say that work was done on a point charge. I was going to say by an external force. Yeah. Oh, what happened? The screen got bigger. Cool. Okay, so yeah, work done on a point charge by an external source. So that's like you with little microscopic tweezers pulling an electron over or something like that. So before and after shot, work was done on a point charge, and I don't want you to use the capacitor. Capacitors are off limits for this question. I'll give you another ready to continue message. Let me know if you have questions. And yeah, have fun. Okay, so it looks like we're ready to keep going with this one as well. Oh, my cat agrees. Okay, so can the owner of this first system with just one single point charge, it looks like maybe it's moving towards a line, can whoever made that system or that diagram explain a little bit what's going on? If you want to unmute yourself and just kind of explain the system, that would be fantastic. If you don't feel comfortable with that, you can type it out too.
I can try to explain it, but what happened was like I kind of couldn't take the second point charge like over, so it just really stopped working. But what I was thinking, that line was supposed to represent before and after, and I was just going to represent like a point charge moving from one place to a further place.
Okay.
Yeah.
Oh, I see what you mean.
Along the arrow, yeah.
Okay. My question for you, in the way that you've drawn this, is, so you're saying since an external force is moving this point charge a certain distance, so applying a force to move it a distance, that does work on the point charge. And your arrow staying the board before and after. Fantastic. Okay. The owner of the second system with the graphs, would you like to explain a bit what you're doing there? Please.
Hi, sorry.
It's okay.
So I wasn't exactly sure how I was going to represent it, but basically I wanted to show a point charge moving from point A to point B, and there's another charge that's in the area that's that has an influence.
This charge here?
Sorry, I'm on the wrong page. Yes, I tried.
Okay. Okay, nice.
I put it in a different color because I wanted to show that it was a different charge. It was not like the same kind of charge. It is not the same charge as the pink dots.
Yeah, I like that. Okay, cool. So you have a stationary point charge, which of course makes an electric field of its own. So that's your blue one. And the fact that you're forcing the pink point charge to go from point A to point B, you have to apply a force on that charge, absolutely, to get it from point A to point B, because otherwise it would either just be straight up repelled or attracted from what you've labeled charge Q. Nice. That's a very nice diagram. I like it a lot. Okay, can the owner of the pirate wheel diagram, it's not pirate wheels, but of this third one, can you explain what's going on in your system?
Well, I couldn't remember if the green circle was like a surface or not, so I just kind of decided to ignore it.
Okay.
But I'm just showing that the potential is changing and therefore the work's changing because it's farther distant. It goes farther distance.
Okay. So if we pretend that the green circle is just like a Gaussian surface or something that's not real, then you're moving a pink point charge away from the charged sphere, and so there's forces acting on it, moving a certain distance, so work is done. Yes. Now, before we move on to the next system that I want you to make, can you write, and you can just like write it, grab a text box and write it out. In your diagram, in your system, does the electric field do positive work or negative work or no work on the point charge? So that's not necessarily you like moving the point charge. The other electric field or external electric field or electric field coming from a different source, what sign of work does it do on your particle or your charge? Yes, I'm glad someone wasn't afraid to use the sun/pirate wheel diagram too. So in your diagram, what would the sign of the work be? You can also think of it as, so positive versus negative versus zero work tells you, does the energy of the system increase or decrease or stay the same? Okay, I see 3 answers here, so we'll start talking about those. We'll zoom in a little bit. Okay, so I'm seeing in this first diagram, work done is positive. Okay, that for what you've defined as your system, the well, there's no, I don't know how to say it. This is weird. So your particle is moving from left to right, but there isn't an external electric field. There isn't an electric field to actually do work on your particle. So if you have to apply a force to move the particle, you can do work on the particle. But since there isn't an electric field, like an external electric field, in like that's included in your diagram here, there actually is no work done on your particle from the electric field. Now, if you apply a force to the particle and the particle moves in that same direction, then you would do positive work on the particle. But since there's no external electric field coming from some other source, then there's no work done from an electric field on that particle. Let me know in the chat if you'd like me to go over that again or in more detail or anything. And for now, I'll move on to, that makes sense? Okay, fantastic. All right, so this, my dog's throwing a tantrum. Okay, this second system here. Okay, so here we have work sub AB. Okay, so from A to B equals 0. It's actually not 0 because you do have a charged particle in the presence of an external electric field. So in this case, the external electric field is coming from your blue particle, your blue charge Q. So your pink charge, your positive charge, is in an external field. So, oh, wait a minute. I just noticed something. The designer of this system when the particle is at point A and point B, is it meant to be the same distance away from the blue charge Q? Yes, it is. Okay. Okay, you can forget what I was saying before then. Yes, absolutely, the work done here is 0. Okay, thank you for clarifying that. So yes, since your charge, well, okay, I guess you can look at it like, just one moment. Okay, I'm back and the dog is happy, for now anyway. So, okay, so the work done on the particle is equal to its change in potential energy, as the designer of the pirate wheel system has so helpfully included here. So, in this middle system, the pink charge, blue charge system has a certain electric potential energy at point B and another potential energy at point when the pink charge is at point A. But since the distance between the two charges is the same in both those positions, then the potential energy would be the same in both those positions. So the work done to go from one point to the other point would be 0, because the potential energy, the electric potential energy overall did not change. Nicely done. Of course, if these weren't the same distance apart, if these both were the distance r, then there would be work done. Okay, nice. So now on to the pirate wheel diagram. So the change in potential energy is equal to the minus of the work done on the particle. And you're saying, so the final potential energy is less than the initial potential energy. Yes, because two objects with the same sign of charge have moved further apart. So their potential energy decreases, which means, so delta U is negative, which means the work done is positive. Yes, absolutely. Another super quick way you can check, and it works especially well on this pirate wheel diagram because you have some electric field lines, is that electric field lines, the way that we've decided to draw them, they point in the direction that a force on a positive object would feel. So your pink particle is in this starting spot, kind of on an upwards pointing electric field line. So the force on this pink particle is going to be upwards. Its displacement, as we see in the second diagram, is also up. And so since the force and the displacement are in the same direction, that means the work done is positive. If they were in opposite directions, then the work would be negative, and that would work through in the change in potential energy as well. Okay. I want to pause here, see if anyone has any questions, and if you don't have a question, let me know everything's good. And then we'll move on to our third type of system. Okay, looks like we're good to keep going. Thank you, whoever keeps arranging the size of this, the diagrams here. That's super helpful. Okay, so the third type of system I want you to make is a system that is in its preferred potential energy state, or in its lowest potential energy state. And I don't want to say 0 potential energy, because technically you get to define 0 potential energy. And so sometimes we say an infinite distance away is 0 potential energy. Sometimes, I don't know, we define it differently. So what I just said, to be a bit more consistent, is just a system that is in its lowest potential energy state. And for this, I would like for you to only use point charges. Okay, so we have here, I'll give you some more pink ones. So we have the positive pink point charges. We have the negative green point charges. I want you to only use point charges. You can say they're in a box that is, so everyone has like a little square, a little rectangle for their system to be in. We'll pretend that your particles can't escape that system, just so that you don't have to make them go actually an infinite distance apart. So in the box, what's their lowest potential energy state? I also, because I'm going to be really picky because you guys are smart, I would like for you to use 5 or more point charges. Yes, so in the chat, someone said, there goes my idea to use only a single point charge. Yes, that would have been excellent. Just have one charge happily sitting there. That would be great. That's very true. Ooh, we've got a big charge. Oh, and I'll give you another ready to continue message once you have your 5-point charges and you're happy with where they are. Okay, looks like we're ready to continue. So now that our green point charges are no longer feeling neglected, let's see what types of systems we've got here. Okay, so in this first system, we've got 1 point charge, so that's not quite the 5 point charge that I asked for, but having just 1 point charge without any other charged objects nearby, without any external electric fields, like, yeah, that's a pretty low potential energy state. So you're not wrong. Yeah, I guess that doesn't really show a configuration relative to other particles or anything, but you know, 1 charge by itself is absolutely a low energy state. Okay. This second system here. Oh, your computer wasn't working. Okay, no worries. I didn't mean to berate you. Okay. Yeah, no worries about the single charged system, or the single like point charge system. Okay, so the second system here, we've got 3 negative charges and 2 positive charges, and they're all infinitely far apart. So if they're all infinitely far apart, the 3 negative charges are really happy to be far away from each other. That's what they want. The 2 positive charges are also happy to be far away from each other. But what about the interaction between the positive and negative charges? Like the positive and negative would attract each other. So if they have, if they're separated by a really big distance, that would still cause potential energy between them or within them as a system, because they would be attracted to each other. So the pink charges don't want it to be far away from the green one. Think about it that way. Yes, that's a very good point. So if you had used all 1 type of charge, then yes, having them all infinitely far apart would absolutely be their lowest energy state. Okay, I do have one more question, and this is getting really nitpicky with the geometry and things, but there's a bit of a point I want to make. Do you think that your particles would be farthest apart if you have 4 in a square around each other and 1 in the middle? What if you made them into a pentagon shape? Then you wouldn't have this middle one that's closer to the others. I mean, being constrained to a square makes it a bit harder to see. Oh, yes, you can get rid of the comments if you want to. It's up to you. But yeah, actually, what ends up happening in real life, or like, I don't know, real charged objects, I guess, is that if you have a charged object, and it has to be a charged conductor, just so that the charges can move around. Otherwise, if it was an insulator, wherever you put the charge on the object, it's going to stay there. But in a conductor, if you have an excess negative charge, for example, because that's what you have here with all these extra green point charges. If you have an excess negative charge, then the charges to get away from each other, they actually do end up all going on the surface of your object. So even if you have a conductor, a solid sphere conductor that has excess charge, to be furthest away from each other, the charged particles always go on the outside of the conductor. And so that's kind of what you're showing here, is that to be as far apart from other like same charges as they can, they would always go on the outside of their object or container that they're in, or whatever the case. Okay, Nicely done. This third system, we've got a nice, I don't know, this makes me think of a caterpillar, like the alternating dots. We've got negative charge, negative, positive, negative, positive. So this is really favorable in that the negative and positive charges are all close together. That is absolutely what they want to do. But in this configuration, you've still got three negative charges that are all kind of close together and positive charges that are all kind of close together. Do you think maybe there's a slightly different configuration where you could still have positive charges between negative charges, but the similar charges are more spaced out? And that's actually an example of like crystalline structures and things like that, where you have negative and positive charges or poles of a, I don't know, poles of a molecule or whatever. I'm not a solid state scientist by any means, but and kind of like an alternating grid like pattern of positive and negative charges would create that, like, I don't know, like that favorable orientation. Okay. Oh, this is nice. You got your charges separated into dipoles. Okay, cool. So now we have 3 dipoles, and they're spaced apart. So negative far from negative, positive far from positives. Yeah, that might be a more favorable configuration. Okay. What about, so question in the chat says, what about an arrangement of alternating point charges in a linked circle? That's a good question. Okay. So like the caterpillar, but in a circle. You would still have positive charges close to positives, negative charges close to negatives. If they were constrained to a circular object, so if you had a solid conducting sphere, then that you would see something like that. You'd see positive and negative charges alternating, so that positive charges aren't together, negative charges aren't together, and they would be on the surface of your object. So yeah, that would be an example of a low potential energy state. Another example that is seen in different types of crystalline structures is like a checkerboard pattern almost of alternating like alternating positive and negatives kind of offset from each other. That's also something that kind of shows up a lot in nature. Okay, are there any other questions or any other comments about anything we've talked about tonight? If so, put it in the chat. If not, if you're good, then let me know. I'm glad you found the point charges helpful to manipulate. I always find those confusing when you have a lot of little things going on. So yeah, I'm glad that helped. Okay, so everyone's good. Fantastic. This is an awkward timing because we have 10 minutes left, which isn't really enough time to start a whole new set of questions or things. So I think what I'll do is we'll end this recording here with this more visual, conceptual, not project, activity. And in tomorrow's PAL session, I'll set up some calculation type questions and practice examples using the diagrams that you've come up with today, using some of these diagrams. If you can't come to tomorrow's PAL session, just let me know. I'll give you access to the recording. And I can also give you access to my OneNote files as well. So you can see my written work there, even if you don't have time to go through and watch the recording and things. But I think for tonight, we'll end this here and pick it up with a bunch of examples tomorrow. So with that, I will stop the recording.